Okay, let's get started. So today, if we have time, hopefully we have time, we're going to get to the washer method. We're going to cover what we talked about yesterday in a little more detail, which was the disk method, or if you want to call it the coin method, that would also be fine. But after today, you should have everything that you need to be able to do the homework, and it will be glorious. So announcements, you have homework due on Monday. In my office hours on Monday, Wednesday, Friday, 10 to 12. Fridays, which are tomorrow, will be via Zoom. And then there's a discussion post due this week. You just need to take a picture of something that is solid, that has a constant, not a constant, but cross sections that are all some known shape. So for instance, I have a flashlight next to my computer. I have to use it when I take my dog out at night so I can see where she poops. But this has a constant, again, sorry, not constant, but when I take cross sections parallel to the face of the flashlight here, I get circles, right? Every cross section is a circle. Maybe not a circle of the same size, but all of the cross sections are circles. Okay, so take a picture of something like that, post it, and say what the cross sections are. Okay, and then one more announcement that I don't think I put, no, a reminder that Monday is also virtual for everybody. Hopefully that's our last virtual day. I will be traveling that day, but I'll be able to meet with you guys in the morning. So Monday is remote for everybody. Okay, so do we have any questions on these announcements? Okay, then let's pick up where we left off yesterday, and that's in finding the volume of a circular cone. And a circular cone is a cone that, I mean, it's a pyramid shape where the base is a circle, right? So maybe you already know that the volume of this shape that has a radius r in the base and a height of h, maybe you already know that this was pi over 3 times r squared h. And if you do, that's great. I'm so proud of you. But if you don't know, then we can use this method of rotating a region about an axis to find this volume. So to do that, we're going to rotate the region bounded in the first quadrant by this curve, x, y. This curve given by y equals negative r over hx plus r. So that goes through the points 0, r. If x is 0, then y is r. And when x is h, then y is minus r plus r, which is 0. So that's why we're using this curve, because when you rotate this region about the x-axis, well, that's just this region rotated around, and we get a volume of revolution. Okay, so I want to find the volume of the volume of revolution that we get. So again, let's take some little sliver at the x coordinate x, and this little sliver is going to have a width of dx. Okay, when I rotate that little sliver around the x-axis, I'm going to get a disk. Okay, what is the width of this disk? Do the easy one first. Someone tell me the width of this disk.
dx.
Dx, very good. The width of the sliver is the same thing as the width of the disk here. Okay, so then the only other thing we're going to need to find the volume of this disk is the radius. And what is the radius?
The R.
It's R. Well, the radius in the bottom of the cone is R, but I mean the radius.
F of X.
Yeah, very good. F of X. And for us here, F of X is negative R over H times X plus R. So two different uses of the word radius here. I get that it's a little confusing. But the radius of the disk that we get by rotating one sliver is negative R over H times X plus R. So then what's the volume of this little disk? Someone other than Jet. But thank you for answering, Jet. Well, it's gonna be the area of the circle times the width of this disk, right? So what's the area of this circle? This circular base here.
Pi r squared.
Pi times, yeah, r squared. And for us, the radius is negative r over h x. Let me erase this. Negative r over hx plus r squared. So there's pi r squared. And then I'm going to multiply that by dx, right? And that gives me the volume of this tiny little disk. So then if I want the volume of the cone, well, I can integrate this. So I'm going to integrate pi times negative r over hx plus r squared dx. And the only things I need to know now are the lower bound and the upper bound that I'm integrating over. So what could x range between? Looking at this drawing, what are the possible values that x could be between?
0 and h.
0 and h, perfect. X starts off at 0. That's when we're here. And then it could be anything between there and h. So 0 and h. Very good. And then the rest is, well, the algebra and then the fundamental theorem of calculus, right? So I'll pull the pi out in front. This is pi times the integral from 0 to h of negative r over h x plus r squared dx, which is pi times the integral from 0 to h. Now I'm going to square everything. If you want to use a u substitution, you could do that as well. Either way. But I'm just going to square everything. So I'm going to get r squared over h squared times x squared minus 2r squared over h x plus r squared dx. Okay. And then keep in mind that r and h are both constants with respect to x, right? Constants. So when I integrate, that multiplication by r over h or r squared over h squared doesn't really matter. It's just going to, you can pull that out in front of the integral. So we'll do this term by term. I have a pi multiplying everything. When I integrate r squared over h squared times x squared with respect to x, what do I get? Well, like I said, the r squared over h squared is a constant, so that's just going to come along for the ride. What is the integral of x squared with respect to x?
X cubed to divided by 3.
Perfect. X cubed divided by 3. Very good. Then we can integrate this piece. So I'm going to get minus 2r squared over h times, well, what's the integral of x with respect to x? I saw someone say it, x squared, and don't forget to divide by 2. You add 1 to the exponent and then divide by the new exponent, okay? And then plus, well, r squared, again, remember, r squared is just a constant. So I'm going to get r squared, that's just a constant, times x. And I evaluate this at x equals h and x equals 0. Okay. So when I plug in x equals h, what do I get? I'm going to get pi times, well, I'll get h cubed times r squared over 3h squared. So I'll get h cubed r squared over 3h squared. And then minus 2r squared h squared over 2h. 2r squared h squared over 2h. And then plus r squared h. Plus r squared h. And then what do I get when I plug in 0? I think someone said it. It's just 0, right? When I plug in 0 till everything has an x, I'll get just a 0. Okay, so this is what I have after plugging in h and 0. So when I simplify this, these 2's cancel. H squared over h is going to leave me with that. So notice that minus r squared h plus r squared h, those are going to cancel. So I'll be left with pi times, and then here, h cubed over h squared, well, that's going to leave me with h times r squared over 3. Again, that cancels with that. And so we are left with pi over 3 times r squared h, or hr squared, however you want to write it. But we get the formula for the cone, the volume of a cone, that if you knew it from earlier classes, that's great. But if you didn't know it, now you know it. And now you know how we get that volume. So if you worked this problem out after class yesterday, hopefully you got pi over 3 r squared h.
I have a question.
Yeah.
Earlier in the integral,
Yeah.
how'd you get like that minus 2r squared over h on that right side in the middle?
That's just from squaring. If you square a plus b, or really a minus b here, a minus b, you get a squared minus 2ab plus b squared. And so that minus 2r squared h, sorry, 2r squared over h times x comes from minus 2 times that times that. Yeah, April.
Yeah. I had a question about after we started the integral and then we were like doing the x squared over 2 and all those things.
Mm-hmm.
Where did we get that last x after the r squared? Is that from the dx?
Yes, that's from so that's from integrating r squared with respect to x, because r squared is just a constant. So
Okay.
just think about, yeah, if we were integrating 3 with respect to x, we would just get 3x. Same thing here.
Thank you.
Mm-hmm. Any other questions? Okay. So everything we've talked about works almost exactly the same way if we're rotating a region that's defined by functions of y instead of functions of x about the y-axis. Okay, so you can go through and do everything that we did for functions of y, and you'll end up with this. So let me give you a drawing really quick of what this is actually saying. So now if I'm integrating, instead of a function of x, if I'm integrating a function of y, so this will be x equals g of y, and I want the volume of revolution that I get by rotating this region here about the y-axis, rotate So this is in the theorem, I call this region Q, but I take this region, instead of rotating it about the x-axis, I rotate this region that's again defined in terms of functions of y. I rotate that about the y-axis. Then, well, you do the exact same thing. To find this volume, you take one little sliver. Here's a little sliver, but now it's at some y, and it has a width of dy. And then we look at what happens when I rotate just that little sliver, which we'll color in with SU red. When I rotate just that little sliver about the y-axis, well, you're still getting a coin. It doesn't matter that you rotate it about a horizontal axis, right? Or I guess a vertical axis. You still get a coin, and the radius of this coin is just g of y. The radius is g of y, and the width of this coin, or this disc, if you want, is dy, so that the volume just of that little coin is pi r squared, so pi times g of y squared times dy, right? It's the area of the base times the width. And then to get the actual volume of the whole solid of revolution, well, we integrate this. We integrate between y is ranging between C and D. And this is where this formula comes from. Okay. Should have a square. So really not any different. We're just doing things in terms of y instead of in terms of x. But being able to do this is going to give us a tool for future problems. So here's the whole theorem stated out. Again, G needs to be continuous and non-negative. If ever I ask you to find a volume of revolution, that's going to be true right away. Okay, so no need to worry about, well, I mean, you should worry about the hypothesis of the theorem, but when you apply it, that's going to be satisfied. Okay. So any questions about this? Again, it's not really anything different, just y's instead of x's. All right, so an example. Let's find the volume of the solid generated by rotating the region bounded by the curves. Y equals the square root of 1 plus x, x equals 0, y equals 2 about the y axis. Okay, so we're rotating. Here's what this shape actually looks like, by the way. It looks like sort of a saggy cone, I guess. But if I look at what I'm actually drawing, well, y equals the square root of 1 plus x, y equals the square root of 1 plus x. So when x is 0, y is 1. When when y is 2. Okay, so when we graph this shape looks like the normal square root function, but shifted over to the left by 1 unit. Okay, so we're taking that region and we're really ignoring that part, but I'll draw it in so you can see the whole shape. So we're taking that curve, then we're taking y equals 2. And then x equals 0 is the y-axis. So the region that we're rotating about the y-axis is this region here. Okay. But notice, so we've never rotated a region defined in terms of a function of x about the y-axis. And we don't really have the tools to be able to do that yet. So what should we do to figure out this volume of revolution. Because if I'm rotating something about the y-axis, then as of right now, the only thing we know how to do is take a horizontal slice like this, right? And it has a width of dy. So what should I do before I do anything else?
Make it equal to x.
Yeah, exactly right. I need to rewrite this function of x. I need to rewrite it in terms of a function as a function of y. Okay, so this curve, if I try and solve it for x, well, the first thing I would do is square both sides. So I get y squared is equal to 1 plus x. And then the next thing I do is I just subtract 1, and then I have my function of y. I have x is equal to y squared minus 1. Any questions on that? So really, we should rewrite this as x equals y squared minus 1. Okay, and so now I'm taking this coin, or sorry, this sliver, and I'm rotating that about the y-axis. When I do, I'm gonna get a disc or a coin. It has a width of what?
dy.
dy, perfect. And then a radius of what?
Y squared minus 1.
Perfect. The radius is y squared minus 1. So the volume of this little disk is, well, just like before, it's pi times r squared. So that's y squared minus 1 squared dy. So that's a little bit of the volume of the whole thing. So the actual volume is the integral of pi times y squared minus 1 squared dy. Now, I need to know, what does y range between? What are the possible values that y could take on?
1 and 2.
1 to 2. Very good. 1, because when x is 0, that's the intersection of this curve with x equals 0. Okay. And then 2, because, well, that's just this this horizontal line that defines the top of the region. Okay, so 1 to 2. All right, and then the pi can always be pulled out in front. All right, so that's always going to be my first step. So we end up with pi times the integral from 1 to 2. Let me rewrite that. 1 to 2 of y squared minus 1 squared dy. This one I'm going to write, again, I'm going to square everything. So this is the integral from 1 to 2 of, when I square y squared, I get y to the 4th. And then minus 2y squared. So minus 2 times 1 times y squared. And then plus 1 dy. Everyone okay with that squaring? All right, so then we take this piece by piece. What's the integral of y to the 4th with respect to y?
Y to the 5th divided by 5.
Y to the 5th divided by 5, perfect. Minus 2 times, what's the integral of y squared with respect to y?
Y cubed divided by 3.
Y cubed divided by 3, perfect. Plus, what's the integral of 1 with respect to y?
Y.
Y, perfect. Exactly right. I'm so proud of all of you. This is a breeze. All right, so this is going to give us pi times, well, now I plug in my bounds and subtract. So 2 to the 5th 2, 4, 8, 16, 32. 32 over 5 minus 2 times 2 to the third, 2, 4, 8. So minus 2 times 8 over 3, and then plus 2. And then minus, when I plug in 1/5 minus 2/3 plus 1. Okay. So from there, if this was on a quiz, I would ask you to round your answer to the nearest 2 decimal places, because you can't really enter pi into Canvas quiz. But from here, the rest is simplification. So does anyone need me to simplify this guy? Because I mean, it's arithmetic. If you do want me to show you, I can, but I'd rather move on. So technically, by the way, technically this is the correct answer. If you wrote this on an exam, I would give you full credit and assume that you ran out of time. If you can simplify things, you should, but I want to make sure we get to the washer method. So, all right, the washer method. So I lied to you technically when I said volumes of revolution or solids of revolution. You always know that the cross sections are circular. That's almost the truth. But if you think about, again, if anyone's seen a lathe machine or whatever it's called, those spin something and then you shape the outside. But then sometimes if someone's making, say, a bowl, they will come in with some tool and they will start shaping from the middle of the block of wood and shape from the middle out too. And so you'll end up not just with circular cross sections, but with a cross section that is, I mean, think of a cup. If I have a cup with a hole in it, if I take cross sections here, the cross sections aren't actually just circles. The cross sections are these thin little rings, right? Other example, if I have, I mean, if you think of a bottle as well, the cross sections aren't just circles. The cross sections are thin rings. Okay. So let's think about taking a region defined by 2 curves and rotating that about the x-axis for a second. If I take the region bound by y equals x squared and y equals the square root of x, this is x, y. If I take this region here and rotate that about the x-axis, then what's going to happen is I'm not going to just get circular cross sections. Like I said, I'm going to get cross sections that are rings, right? If you rotate that about the x-axis, you'll end up with some shape that it kind of looks like a bowl. It sort of a fat bowl. It'll do something like that. Okay, it'll have a sort of a cavity inside. And when we say we want to find the volume of revolution, we're really saying we want to find the volume taken up by that region. We're not finding the volume of the cavity. We're finding the volume taken up by that region as it sweeps out a solid about the x-axis. Okay. So to find this volume, I'm going to do the exact same thing that we did before. And it's the exact same thing that we're going to do for any really applied problem in this course. You're going to take a little sliver. So I'm going to take a little sliver of this region here at x, and it has a width of dx. And I'm going to rotate that little sliver around the x-axis. Instead of focusing on the whole region, just focus on one small sliver of it. Well, what kind of shape am I going to get when I rotate that little sliver around the x-axis? Well, now I'm not going to get a ring, or sorry, now I'm not going to, I mean, I'm going to get a ring. Now I'm not going to get a disc like before where I had that. I'm going to get a disc with a smaller disc cut out of the middle, right? Does everyone see that? If you take this region that I'm coloring in SU blue, if I take that region and I rotate that around the x-axis, well, there's going to be that gap there the whole way around. Okay. I like to make my drawings as 3D realistic as possible. So, I mean, I haven't formally told you how to find this volume, but what do you guys think is going to happen next?
We find the volume of the whole disk minus the volume of the smaller.
Exactly
cavity.
right. Exactly right. We're going to find the volume of this ring shape by taking the volume of the whole disk, pretending there's no hole cut out of it, minus the volume of that hole. And then what do I do once I find that volume of just this ring here? I'm going to take that volume and I'm going to well, what did we do before? We found the volume of a disk, and then what did we do with the volume of that disk?
Integrate it?
We integrated it, right? Integration, again, we're sort of jumping over the fact that we looked at Riemann sums, but we're going to do the same thing here. If you want, you can look at this in terms of Riemann sums. But from now on, when it's possible, I'm just going to jump straight to integration. So I'm going to find the volume of this. This shape is called a washer, by the way. You can call it a ring if you want. It's called a washer from the little pieces that if you're putting a bolt onto something, you put a washer on to protect the object from getting scuffed up. Okay, so we find the volume of this washer, then we integrate that. Okay, so the volume of this washer in particular, I'll call it dV, is going to be, well, it's exactly like Mark said. I'm going to find the volume of, let's pretend that there's no hole in this shape. Then what would that volume be? Well, just like before, it's pi times the radius squared. So what is the radius of the bigger circle? Well, that's going to be that distance from the x-axis up to the top curve, right? What is that distance? Yes, Mark said it, but he's muted, but I heard it in spirit. That's going to be the square root of x, pi times the square root of x, and then squared dx. So that's the volume of the bigger disk, pretending there's no hole in it, right? Then let me move this so I have space. Then I'm going to take the volume of the smaller disk that's cut out of that and subtract it, right? So minus the volume of, let me erase this also. Minus the volume of the smaller disk. So again, that's going to be pi times the radius of the smaller disk. So the radius of the larger disk was the square root of x. What's the radius of the smaller disk? X squared. Exactly right. So I'm going to take minus pi times x squared, and then I square that because the radius is x squared. I want the volume, which involves the area of that circle. So pi x squared squared dx. And so then notice I can rewrite this. Both of these have a dx in them. So I'll factor that out. And I end up with, oh, they also have a pi. So I end up with pi times square root of x squared minus x squared squared dx. And so now I can integrate that to get the volume. I'm going to get pi times the square root of x squared minus x squared squared dx. Now the only thing I need to know is what are the possible values of x? What could x be between? What do we think from this graph? I know I didn't label much, but one of the points should be obvious.
0 is one of them.
0 is definitely the bottom bound, right? And how would I find the top bound?
Set them equal to each other.
Exactly right. The top bound, that's where x squared is equal to the square root of x, right? So where is x squared equal to the square root of x?
That just be 1 in this case.
Yes, this one is just going to be 1. Okay. Very good. So I've avoided simplifying this so far, but this is actually simplifies very nicely. The square root of x squared is just x, and then minus x squared squared, that's x to the 4th dx. So this gives me pi times what's the integral of x with respect to x?
X squared divided by 2.
X squared divided by 2, perfect. Minus the integral of x to the 4th with respect to x.
X to the 5th divided by 5.
Perfect. X to the 5th divided by 5. I'm going to plug in x equals 1, plug in x equals 0. And when I do that, I end up with pi times, well, when I plug in 1, I get 1/2 minus 1/5. And when I plug in 0, I get 0. So this is my answer. And you can simplify this to 3 pi over 10 by, again, getting common denominator and all that jazz. So even though I haven't even formally told you how to handle shapes like this, what we've done before really naturally carries over. And again, this idea of taking, instead of focusing on the whole region, take one slice and see what happens. That method, that process is so useful, and you can apply it to most problems, most applied problems in this course. Okay, so this, what we did, you can generalize the method and you'll find the washer method. So this is this shows that the cross section of solids of revolution are not always just circles. You're going to get washers, which again, the cross sections are going to look like in general, instead of just a circle with a smaller circle cut out. That's a washer. Okay. So when you do this process, you're going to find that the area of that circle that I just drew, we just found that it's pi times the big radius squared minus the little radius squared, right? And so that naturally leads to the washer method. And this is, notice this is exactly what we just did with specific functions, but I mean, the process works exactly the same way every time. Okay, so if f of x and g of x are continuous, non-negative functions, and f of x is bigger than g of x on the interval a to b, then letting R be that region between f of x and g of x, and we're assuming this is between x equals a and x equals b, the volume of the solid that you get by rotating R about the x-axis is given by this integral here, pi times f of x squared minus g of x squared. Now, something to be careful about. Careful. My Spanish teacher used to always go, cuidado, but I don't speak very much Spanish. But warning, careful. Do not ever write the integral from a to b of f of x minus g of x squared. This is not the Washer method, okay? When I was learning the Washer method, I would periodically forget that it was this, and I would take f of x minus g of x, and I would square that. That's not going to give you the right answer, okay? And so some people prefer to memorize formulas and apply them. I really think doing a quick sketch of what's happening and drawing a little sliver and seeing what happens with that sliver, it adds maybe 10 seconds to the problem, but it makes it so much more clear what you need to integrate. And so it might annoy some people, but I'm always going to draw a little sliver and see what happens instead of just jumping to this integral. Okay, so that's the Washer method. Let's look at an example. So find the volume of the napkin ring generated by rotating the region bounded above by y equals the square root of 4 minus x squared and below by y equals 1 about the x-axis. And again, with the napkin ring, we're not finding the volume of the cylinder that's been cut out. We're finding the volume of everything that's left over. Okay, so we're finding the volume inside of the napkin ring, not of the cavity that's left. Okay, so again, I'm always going to sketch a graph of the region that we're rotating. So y equals the square root of 4 minus x squared. What is that curve?
Is that like a half circle?
Yeah, perfect. 1, 2, 1, 2. This is a half circle with radius 2. And the way we can see that is square both sides. We get y squared equals 4 minus x squared. So x squared plus y squared equals 4. Notice before we were taking the positive square root. So that means y has to be positive, and I'm looking only at the upper half of this circle of radius 2. Okay, y equals 1 is this curve right here. So I'm taking this region bounded by those curves, and I'm rotating it about the x-axis. Okay. So what do? We take a little sliver. We take a little sliver here at some x, and we look at what happens when we rotate that little sliver around the x-axis. Okay. So when I rotate that little sliver around the x-axis, what are we going to get? Well, we're going to get a disk, a big disk from when that curve is rotated around the x-axis. But then we're always going to have that gap on the inside, right? We have this gap on the inside. So we have some inside radius and some outside radius, and I'll call the width of this thing dx. Okay, so what is the inside radius?
One.
1, perfect. It's 1 all the way across. So the inside radius there is 1. What is the outside radius?
The square root of 4 minus x squared.
Perfect. Square root of 4 minus x squared. And what is the width?
Dx.
Dx. Perfect. You guys are nailing this. So the volume of this washer is Well, again, it's pi times, take it in pieces, the big disk without any hole cut out, the area of that circle would be pi times 4 minus x squared square root. That's the radius, and then I square it, right? And so the volume of that disk with no hole cut out would be this. I never give myself enough room. Okay, but then I need to subtract pi times, well, that hole that's cut out, that's going to have a volume of 1 squared, or sorry, it has a radius of 1. So the volume of that hole that's been cut out is pi times 1 squared dx. And so I can rewrite this as, you always want to only have a single dx. Okay, so, but with this method, you'll always be able to factor out the dx. So you're always going to, in this case, I'm going to have pi times, well, the square root of 4 minus x squared is just 4 minus x squared. And then minus 1 dx. So there I factored out both the pi from both terms and the dx from both terms. Okay. Questions before we do this integral? Okay, let's actually compute it. So the volume of this napkin ring is going to be the integral from somewhere to somewhere. We'll find those bounds in a second, but of pi times, well, 4 minus 1, scientists say that that's 3. Well, I'll simplify it in a second. 4 minus x squared and then minus 1 dx. Okay. So we need to find the bounds here. So x is ranging between what two values? Or how would I find the two values that x ranges between?
You set them equal to each other.
So, yeah, I set what equal to each other?
The square root of 4 minus x squared and 1 equal to each other.
Good, exactly right. To find those points of intersection, I set 4 minus x squared, the square root, equal to 1, right? So to solve this equation, I can square both sides. I get 4 minus x squared equals 1. And then I can add x squared to both sides. I get 4 equals 1 plus x squared. So x squared is 3. So x is plus or minus the square root of 3. Okay, so we have a lower bound of minus the square root of 3 and an upper bound of plus the square root of 3. And now we integrate, because now I am going to simplify. 4 minus 1 is just 3. So we're integrating 3 minus x squared dx. So when we do that, well, what is the integral of 3 with respect to x?
3x.
3x, very good. And minus, what's the integral of x squared with respect to x?
X cubed divided by 3.
X cubed divided by 3. Perfect. And now I plug in x equals square root of 3. X equals the minus square root of 3. And I get pi times 3 square root of 3 minus square root of 3 cubed over 3. And then minus, really the negative of that, minus 3 square root of 3 plus square root of 3 cubed over 3. And this looks pretty nasty, but it actually simplifies pretty well, because this is pi times, really, this minus this is going to give me 2 times the first bit. So let's just focus on this for a second. We're going to get 3 square root of 3 minus the square root of 3 cubed. That's the square root of 3 times the square root of 3 times the square root of 3, then over 3. So square root of 3 times the square root of 3 is just going to give me 3. And then those cancel. So 3 square root of 3 minus 1 square root of 3 gives me, I have a 2 pi out in front, 2 square roots of 3. So I get 4 times pi times the square root of 3. Amazing. Any questions on this one?
How did you get 2 pi again?
Yeah, the 2 pi comes from this minus this. Well, this is the negative of the first bit. And so some a minus minus a is 2a. So that's where that comes from. Other questions? All right. Excellent. So we will pick up here on Monday, and really all that's left to talk about is just doing this same exact thing, but about the y-axis. So I do think you have everything you need now to do the homework. So if you guys have any questions about any homework problems or anything like that, let me know. I'm more than willing to help. But other than that, have a fantastic weekend, and I will see everybody on Monday. Thank you all for being here, and thanks for being so responsive.